Here's a target. Model and solve problems involving money accumulating continuously and population growth. And we're going to do this with the exponential and or logarithmic functions. Before we jump to the blackboard to work a few examples, let me walk through two definitions with you. So continuous compounding. If interest is compounded continuously at annual interest rate R, then after t years, an initial amount P naught grows to P of t equals P naught times e raised to the RT. And the reason for this definition is a little beyond the scope of our course right now. We can use it easily, but the logic behind why we get that e when we're doing continuous compounding, we will do that with limits next semester in Calc 1 to show you why this definition holds. So one more definition, we'll see. I'm going to work through the example in a minute. So here's the continuous growth rate. If a quantity has a continuous growth rate of R per unit time, then after T time units, an initial amount P naught grows to, and you see here it's the exact same thing as money growing continuously. Anything growing continuously is going to have this form. Okay, so now let's jump to the blackboard and work through a couple examples. Alrighty, here's the example. That's example 2. Example 1, let's see. How many years does it take for money to double at 5% annual interest compounded continuously? So let's note first that we have the formula will be P of t equals some initial amount P naught times e to the r, and our r is 0.05 t. Okay, and now we need our our initial investment P naught to double. So that means I will have I need to find the time t such that my money has accumulated to 2 P naught. So equals P naught times e to 0.05 t. Okay, and now we have a common factor of P naught on each side, so let's divide out by P naught on both sides and get rid of that factor, and we have 2 equals e to 0.05 t. And now anytime we have a variable that we need to solve for up in an exponent, we want to use our logarithms. So here the obvious logarithm to use is the natural logarithm. So we can take the natural log of both sides. You can do anything you want to a math equation as long as you do it to both sides. So I'm going to have the ln of 2 equals the ln of e raised to 0.05 t. But of course this right hand side here is just, we know that that's 0.05 t. So ln 2 equals 0.05 t. And then we divide out by 0.05, ln 2 divided by 0.05, and we get t is approximately equal to, let me punch this in my calculator, on clear, so I need the ln of 2 divided by 0.05, and it's, look, I'm getting 13.863, so 13.863. So I would state my answer. Therefore, the money will double in about 14 years. Let's say that. Okay? Let's go to the next example with population growth. Here it is. Suppose that a colony of bacteria has continuous growth rate of 10% per hour. By what percent will the colony have grown after 5 hours? So let's get our function. P of t equals P naught times e to the RT, and R is 10%, so it's 0.1 t. Okay? by what percent will the colony have grown after 5 hours? So we're looking at P of 5. P of 5 equals P naught times E to the 0, let me put that 0 because it don't look good, 0.1 times 5. And so this is going to equal P naught. Let's get a decimal approximation for E to the, what, 0.5? Let's see, second E raised to the 0.5. You're getting 1.648. Let me, or 1.649. Okay, that 1.649 is my decimal approximation to E to the 0.1 times 5. So what does this mean? This means that after 5 hours, we started out with P naught, and now we have P naught times 1.649. And if we're interested in a what percent will the colony have grown after 5 hours, we know that to multiply something by 1.649, and let's round out to 1.65, we know that we have the initial population P naught has increased by 65%. Therefore, that's what it means to multiply something by 1.65, is that you're increasing it by 65%. So therefore, the population has increased by about 65%. Alright, and thank you. That's going to do it for this video lesson.